sounds good. Yeah. All right, welcome everybody. I'd like to introduce you to Professor Vaswani. He's from Simon Fraser University. He got his PhD from the University of British Columbia, or UBC, in 2018. Then went to Mila, so it's, as many of you might know, is one of the top AI organizations in Canada. Afterwards, you worked at, or you got a postdoc at University of Alberta with one of the godfathers of reinforcement learning. And then since 2022 has been at Simon Fraser University. And really prolific. If you look at his research publications, he does a lot of reinforcement learning, generalization-bound stuff, publishes regularly in NeurIPS, ICML, AI Stats, all the top conference proceedings or conferences in the field. So thank you very much for coming. I'll get to it.
Perfect. Thank you for the introduction and for the invitation. So today it's going to be policy optimization in reinforcement learning. So let me just set it up. So reinforcement learning more broadly is sequential learning via trial and error. So here is this example from 2015 when DeepMind was training Atari games. So this is initially when you have just started training. And the way it works is that the algorithm has no idea about the rules of this game. Okay, so it has to infer everything from this image, which is an image of, like, say, pixels. It figures out that is the score it cares about, and it has to try and maximize the score. Okay, so this is then, it has just started. And then you start training it for a while, and now as you can see, it is starting to get better. The scores have started to increase. So every time a pixel of corresponding to the score increases, you give the agent a reward. And because of that, because the agent tries to maximize it, the scores start getting higher. And finally, after training it for, I think, 2 hours, it figures out that a good strategy is to, like, tunnel through so that it can hit all these bricks. Okay? And that's what we as humans also kind of figure out. And all of this is without knowing the rules. So this was one of these initial applications which got everyone excited. This was also around the time when DeepMind was building the system that beat the human champion in Go. And across the years, there have been many nice applications. So this one is again by Google, which is you want to keep this balloon close to this target in green. And the idea is that this balloon can broadcast, say, Wi-Fi signals. Okay? So you want to be around this vicinity, and it can adjust its altitude, but it can't move laterally. So it is affected by the wind currents. So what they did, they built this RL system in which you get a reward when you're close to this area, this base station, and then the algorithm figures out which currents I should catch so that I remain around this. Okay, so again, this was like via trial and error. And currently, the more exciting application is to these large language models, specifically in aligning them. So the way it works is that you train this some large language model, and you get to this pi-ref, which is some policy or some model which can generate sentences very well. So it can, like, imitate human language, and it's doing a good job, but it hasn't kind of figured out what humans prefer versus what they don't like. So what these systems, including ChatGPT, do, they collect a bunch of preference data where they say, is this response better than the other response? Okay, and if you've been playing with ChatGPT, you would have seen such questions come up once in a while, that is this response better than that? And then what they do is they use this data to train a reward. So the reward is higher for if the algorithm picks answers that are preferred by the users. And once you have a way to quantify the reward, they actually run an RL algorithm to maximize this reward. So you're training this model to bias towards answers that are preferred by humans. Okay, so this is like a new exciting area of research in RL. And finally, we have this robotics example going back a few years. So you want this robot to stand up. So what people in control do, they design these hand-designed actuators of how this robot should get up. but if you train it using RL, it discovers like weird strategies, like this very unconventional way of getting out. Okay, so this is like another application where RL is used to find these behaviors which are kind of novel compared to what we already know. Okay, so given that RL has been used for these applications and the applications keep growing, what our group at SFU focuses on is, can we build robust, efficient, but theoretically principled RL algorithms. Okay, so we want them to work in practice, but at the same time we want them to have like some type of theoretical guarantees so that they do what we tell them to do. So that's going to be the outline for today. I am just going to set up the problem, tell you something about policy optimization, and then I will describe a framework on how to scale to these large problems like Atari games in a principled manner, and describe this algorithm that we came up with. Okay, any questions at this point? Yeah, okay. All right, so let's set it up and do it via this Markov decision process framework, which is the standard setting to describe these RL problems. Okay, so this decision process is composed of 4 quantities. One is the set of states. So in this example, there is this agent that needs to move towards this green box, and it gets burnt if it hits this red one. Each grid on this example is corresponding to a state. Okay, so the agent kind of knows where they are at, and the actions are how it interacts with the environment. Okay, so in this like simple example, it can go up or down, left or right. If it has a wall next to it, it can't go past the wall. So that's the set of actions. Okay. The third thing is this set of transition probabilities, and this models some like stochasticity in the environment. So maybe the actuators of this agent are not very good. Suppose it says I want to move go up. Maybe there is with some probability the agent actually moves down. Okay, so there is like some noise which can make this agent do weird things, and all that is modeled by this set of transition probabilities, which can be given as P of S prime given SA. So this means what is the probability of jumping from state S to S prime if I take an action A in that given state. Okay? So, and then the fourth object is the set of rewards. So the agent here, if it moves closer to the place where it wants to go, you give it like say a positive reward. So the reward is in a given state, if I pick an action and that action is beneficial to me, I'm going to set it up so that the reward is going to be higher. Okay, so in our LLM example, if it prefers an answer which is liked by users, you give it a higher reward and to bias it towards getting higher rewards. Okay, so that's the setup. So for this example, for say when it hits the green square, it should get a reward of like say plus 100. If it hits the red square, maybe like a minus 100. And because you want to maybe make it go as fast as possible, every other time you give it a reward of minus 1, so that it does not like dilly-dally and just like keeps going around without reaching the goal. Okay, so that's how people bias these agents to do the things they want. Okay, so what is the interaction protocol? It's like in every state that the agent is, the agent takes a particular action. Then the environment says, okay, with this action, because of the stochasticity, it might transition to one of these other states. And then you get a corresponding reward according to what action you took in which state. Okay, so that's the setup. Any questions about this? So this is standard MDP. I'm just setting up the notation. Okay, so what is the object that we actually care about? The object we care about is called a policy. It models the agent's strategy. So for example, in this like Mario game, it says, okay, whenever you see like this question mark, you should like jump towards it and get like some reward. Okay, so the thing, the symbol is going to be pi. Pi of A given S is the probability of taking an action A in a state S. So you want to take actions in states which have higher rewards. And because these are probabilities, they are all non-negative and they sum up to 1 for every state. Okay, so for every state, they have to take like at least some action. So what is the objective? So the objective is this thing called the value of a policy. Okay, so the way the value of a policy can be modeled, it can be done in many different ways. One of them is using this discounted cumulative sum of rewards. Okay, so let me parse this for you. So this is an expectation over all the trajectories gamma generated by the interaction. And by a trajectory, I mean I start in a given state, I take an action, I move to another state, take another action. So I keep interacting with this environment and I generate this trajectory of states and actions. Okay, so like over this entire sequence of states and actions is all of this is summarized in this gamma. Across this interactions, every time I go to a state S tau, I take an action A tau, I get this corresponding reward. And I'm going to just discount this by a factor of gamma. So this models the fact, and gamma is something between 0 and 1, and this models the fact that short-term rewards are probably more important than like rewards like far into the future. Okay, so you're going to say maybe $1 today is worth $10 like 2 days from now. Okay, so this models this behavior. So you want to emphasize that you want to earn rewards as soon as you can. So I'm going to discount these rewards which are far away. And I'm going to start as some fixed state S0. So this is like, say, the starting state of this like Mario game. Okay, so across these interactions, so say they are like infinite, you can just like cut them off if they are not. But in the more general case, they are just like infinitely or continually interacting with this environment. Every time you take an action, you get a reward, and that's what gives us J pi, which is the value of this policy. Okay, and this is going to be the kind of main thing we are going to try and optimize for. I want to maximize the rewards across the interactions, and that's the thing I care about. Okay. Any questions so far? Okay, all good. Okay, so now let me focus on this policy that I want to optimize. So a simple way to write it is to just write it in math. Okay, I want to maximize J pi over the set of all feasible policies. Okay, so this set capital pi is the set of all feasible policies. So for example, if you are like Mario, maybe you can't go through a wall, you can't hit a tortoise. So these are the policies that you restrict this class of policies, that you can't do arbitrary things, and this is given by capital pi. Okay, so now as a function of this policy, so remember the policy tells you what action to take with what probability in every state. You roll this out, you get this J pi, which is the cumulative reward. So this is like a very difficult optimization problem to solve. Okay, so it's like non-concave, maybe non-smooth, so it's like kind of tricky. Okay, so in machine learning, the standard approach to solving difficult optimization problems is to ignore all the difficulty and do gradient descent. Okay, so that's like the basic approach. So I want to see if I want to do gradient descent on this objective, what is like the simplest thing I can do? Okay, and the simplest thing I can do is exactly, I start from some policy pi 0, and I'm just going to do gradient descent. Okay, so this nabla J pi t is the gradient of this objective evaluated at pi t. So it is telling us what is the direction to move if I want to go uphill. So I want to move in that direction, and I want to move with a certain size of the step, also called the step size. Okay, so this is like going to be given by eta t. So the gradient ascent procedure is that at any point pi t, when the policy is t, I'm going to iteratively keep updating my set of policies. Okay, so I'm going to start with some initial policy, move in this direction of the uphill gradient, and then I'm going to project such that I ensure that these are actually valid probabilities. Okay, so I can't get probabilities like 2, 5, or -2. So I'm going to ensure that they are all projected onto this simplex, which is delta, which is just like they have to be valid probabilities. Okay, and the way I've set this up is that this pi t is now s times a dimensional vector, where s is the number of states and a is the number of actions. So in every state, I need to figure out how much probability you place on every action. So I'm just going to write this out as like a giant vector of size s times a, and I'm going to update my policy iteratively. So t is like the iterations of this like policy gradient algorithm. Okay, so this is policy, the simplest possible thing you can do. So I have swept a lot of complexity under the rug. It's one of them is how do I even compute this gradient? Okay. So any questions at this point?
Quick question. When the projection operator, if you have other complexities state space. So let's say they can't go to a state. Those constraints are also included in the projection operator?
You can, but for the simplest case, let's just say that we want it to be just summing to 1. Yeah, yeah. Or the other way is that you just bias it, do it via the probabilities, like the transition probabilities.
Right.
That's the other way to do it. Question?
Okay. You say that the policy is a S by a dimensional vector.
Yeah.
Where each cell is the probability of transitioning. Sorry, what is it cell? Is it the probability of transitioning to a given state given an action, or the probability of taking the action given the state?
Taking the action. So it's like a strategy, right? It's like the policy is like, what is my policy when I encounter a particular state?
Okay. But that constrains the design of the reinforcement learning agent, one that takes discrete actions, right?
Yeah, so today everything is discrete.
Oh.
In general, this can be generalized, yeah. So I did not want to throw a lot of integrals, yeah. Yes.
Okay.
If J is not differentiable, you approximate?
You take a subgradient, say. So if you have, if you have some non-differentiability, there are many gradients which are lower bounding the function. So you take one of them and pick a subgradient.
And it's an approximation.
It's exact. So that is exact. The problems we will do today, the gradient exists, and actually I will show you on the next slide what it is. Okay. So, all right. So what is this gradient? So let me just rewrite this update in a more RL fashion. Okay, so this says for every state and every action, I am going to update my probability by taking the probability from before and adding to it this Q pi t SA. Okay, so what is this object? So this is the gradient of J, related to the gradient of J, and it measures the benefit of taking action A in state S and then following this policy pi t. So if I am in a given state, what is the quality? So think of Q as what is the quality. What is the quality of taking an action A in a state S and then from then on following the policy pi t. Okay, so it's like a one-step thing. And of course, if you have the quality of a particular action is very high, you want the probability in that action to also be high. Okay, so it's like proportional. So greater the Q pi t, greater is the step size of the step you want to move for that particular action. Okay, and again, you just take a size of eta t and project it back to the simplex. The simplex, remember, ensures that the probabilities are all normalized. Okay, non-negative. Okay, any questions about this? Okay. So the cool part is that this Q pi t can be estimated using interactions. Okay, so what people typically do is that if I go to a particular state, I take this action and then follow the policy pi t for like a long horizon, I can tell you what are the rewards I accumulated along the way, and that becomes the quality of taking this action in this state. Okay, so you can just like interact with the environment and learn what are these Q pi t's, so you can estimate them by interaction. Okay, so the gradient can be estimated by interaction, and once you have the gradient, you can just update these probabilities in like the simple way. Okay, so this is like the core of this policy gradient method. Okay, so let me write this in yet another way. So this is a different way of writing the same update. So all three updates I showed you are all exactly the same, but they're just different interpretations. So this one is saying, I want to find the policy pi, which is, remember, this SA dimensional vector, which is the most aligned with my gradient direction. And I don't want to move too far away from what I started off. So I want to remain close to the previous policy, but move in this gradient direction. And how close? Well, it is given by the step size. So if the step size is very small, this 1 over eta is very large, so this regularization that I don't want to move too far is going to be very large. Okay, so this is exactly the same way of writing this update. Okay, so in practice, people don't use this method, and there are two reasons mainly. Why? One is that you need to solve this projection problem. So this is all well and good. So solving this projection problem might be kind of annoying. It takes like n log n time, where n is the number of states. And then the more philosophical reason is that the Euclidean norm is kind of unnatural for measuring distances between probabilities. So just think about point 1 to point 2. The change in probability is 0.1, but 0.98 to 0.99 is also a change in probability of 0.1. But the semantics of this is like pretty different. One is like I doubled my probability. One is like I went from 0.98 to 0.99. So probabilities in this sense are not usually naturally expressed in terms of this Euclidean norm. So that's the more philosophical reason why we are not going to use this update, and this results in like poorer performance compared to the algorithms that people actually do use. Okay, so any questions at this point? Okay, so let me move on. Okay, so how do we measure distances between probabilities? Okay, so the standard way is to do it in terms of the KL divergence. So if you have distributions P and Q, the KL divergence is given by summation Qi log Qi by Pi. So this is pictorially, if the probability P is this orange curve, say it is some bimodal distribution, if I minimize KLQP, the Q will cover one mode of this distribution. So P is some like complicated probability. Q covers one mode of them. The KL divergence is asymmetric, and it is always greater than equal to 0. Okay, and it is equal to 0 only when Q is equal to P. Okay, so it is like kind of normalized. It starts at 0, and as soon as you deviate this distribution Q from P, the KL divergence increases. Okay, so the idea is that because the Euclidean norm was maybe not a good metric in measuring distances between probabilities, what we will do is I'm just going to change the way I measure distances between probabilities. Okay, so I'm going to keep everything else the same. So I want to try to find the policy which is most aligned with the gradient of j pi t. But now when I say I want to remain close, the metric for measuring closeness is going to be this KL divergence. Okay, and that's the only change I made. And this, in some sense, is a more natural thing to do. And actually, this update is called a natural policy gradient. Okay, so the natural comes from like kind of this intuition. Okay, so this is like a kind of a very optimization way of writing it. So if I do the same thing, let me just solve this problem and rewrite it in terms of RL. So what I get is pi t plus 1. So the probability after taking the step is the probability before taking the step multiplied by the exponential of the step size times the Q function. Okay, so it has the same semantics. If QSA, if the quality of taking a particular action in a given state is large, this exponential Q pi t is going to be large. So the probability that is multiplying, so the number multiplying this pi t is going to be large. So pi t given A given S is going to be large. Question?
Why is the convention to use the KL divergence versus, let's say, Wasserstein or something else?
So mainly because it gives you like this nice closed form. So with Wasserstein, I don't think you get a closed form. So that would be one of the reasons. But people have started doing that. Yeah. It's unclear how well it does. Okay, so another thing is that your ZT is some normalization factors. Okay, so it just like ensures that all these probabilities, when you add pi t plus 1 up, they all sum to 1. Okay, so it's like explicitly normalized by this numerator. So when you add it across the actions, they sum to 1. And because this is a probability, this is greater than equal to 0. This exponential thing is also greater than equal to 0. So this entire thing is greater than equal to 0. So there is no projection required. Okay, so that's what we have done successfully. We have now made it a natural policy gradient, and now I have an update that is like easier to implement. I just calculate this Q pi t, take an x, multiply it by one number, and that's it. Okay, so this is came around in 2002, so it's been a couple of years, and this is like one of the standard methods. So any questions at this point? Okay, so final thing to set up everything is that all these algorithms, you might have noticed, is that I was creating these vectors pi which were of state size, number of states times number of actions. Okay, so this is like obviously very large, especially if you have large state action traces. Okay, so like in my Mario game, every image that I get is a particular state. So every configuration of pixels leads to a particular state. So I cannot definitely have a probability vector for every state and action. Okay, so that's going to be tricky. So the idea is to use some sort of function approximation, say a linear model or a neural network, to parameterize this policy. Okay, and then the intuition is that all of these states, they are not completely independent. Like if I have a state in the Mario game and I jumped, the state before and the state after are related. So it's not completely different. So I can share information across these states, and the way I will share information is through some machine learning model referred to as F.
Yeah, just trying to get an intuition on the previous slide. So you kind of motivated the regularization by the computational cost of the projection. But, so you've gone from n log n to n, basically, is that right? Because you have normalization, which
Yeah.
is a win, right? But is there something else going on? So you're also not going directly in the gradient direction, it's regularization, so you can deviate from the gradient direction.
So
is that also a desirable thing that you're trying to
So this step that you are taking eventually is like a preconditioned gradient. So you take the gradient, you multiply it by a preconditioner, and that's the direction in which you move.
Yeah.
And the intuition is, if you did not have this preconditioner, you would encounter something flat. And now this preconditioner makes it kind of curved. So you can take gradient steps which are easier, so you will converge faster. That's roughly why this kind of helps. So in practice, it does converge faster. I have an example in like one of the backup slides, but yeah, maybe. Yeah. Okay. So function approximation. So as I was saying, that these states are not independent. So you want to like couple them and share information between states and share information between actions. So the way to do it is through this machine learning model. So what we will say, I will care about only policies that can be written as some output of f of theta, where f is some, say, neural network, some linear model of my choice, and theta are the parameters of that model. Okay, so this model f of theta is going to output a set of probabilities pi, and instead of living in this space of probabilities, I only care about the space of theta. And the expectation is that this dimension of theta is far less compared to the dimension of these policies. So log linear policies is one kind of common way to do this. So it says, suppose I am given features for every state and action. Okay, so suppose I construct, when I look at a Mario game, every scene I can construct features for it, and these are given by x. So I will only care about policies that can be written as exponential or proportional to exponential of this feature multiplied by this parameter theta, and this parameter theta are d-dimensional vectors. Okay. So the search is only over policies that can be succinctly expressed in this way. So instead of looking at all possible policies, I am just restricting the space. I am going to look at only policies that can be written in this way. All of these guys share information. They are coupled via this vector theta. So if I can learn a vector theta, I not only learn what is pi of a given s in one state, I also learn it for like every other state. So we are like coupling everything using this parameter theta. Okay, and this makes it sort of an easier problem to solve. Okay. Any questions at this point? So this was what is going on in this field, and now let's see what is not good. Okay, so the way to scale to large problems is usually to make surrogates. Okay, so we want to maximize j pi. J is a function of pi. I have my machine learning model. What we want to do is I want to optimize over the sequence of surrogate functions LT. This T is the same T as before, it's the number of iterations. And the hope is that if I maximize this surrogate over theta, I indirectly maximize the thing I actually care about. So that's like a reasonable thing, that I am optimizing something which is a smaller dimension, so it only depends on theta, say only d parameters, and indirectly I am trying to, it informs me of how to maximize j pi. Okay, so all famous RL algorithms, including the one whose Atari game, which was playing the Atari game, fall under this class of algorithms. Okay. So it's pretty rich, but it has some problems. So unfortunately, the standard surrogates that people use do not have this guarantee. Okay. So at some point there is, this started off with some theoretical exercise, and over the years people refined this to get better and better performance, but at some point it has so happened that there is no connection between LT of theta or j pi, or like a very weak connection. Okay, so that's not going well. And then because of this, you require like heuristics, like implementation level hacks to make things work in practice. Okay, so if you know about RL, it is like kind of notorious for not being reproducible. There are like many things that you need to do. So this is summarized, say, for example, in this blog post from 2022, which has like 37 implementation details of this like famous algorithm which people are now using to align your ChatGPT models. Okay, so that's not going well. And every time we do a hack, we have to go test it. It's like a lot of compute, so it's kind of not good. Okay, and designing these surrogates that we are using currently is kind of ad hoc. So that was the motivation for this first paper that we did, which was, can we figure out a systematic way to generate such surrogates which have some desirable property. Okay, so let's start with this like NPG example, and I will describe what is the framework we use and then how we can guarantee something which is theoretically principled. Okay, so the NPG update from 2 slides ago is stay close in the KL, move in the gradient direction, optimize over the entire simplex. Okay, and this is SA dimensional. So what I will say, let me construct this class of policies, where all policies that can be expressed by this model F. Okay, so remember, it's like I don't care about any other policy except for the ones that can be expressed by this model F. So for any policy I care about, I can find a parameter such that that policy can be output from this model. Okay, so that's the only set of policies I care about. So I'm just going to slightly modify it. So instead of optimizing over everything, I'm going to only optimize over this class of policies. Okay, so that's it.
So F is guaranteed to generate valid probability.
Yeah. So suppose there is like some soft max at the end, so it's going to generate like valid probabilities. Yeah, that's a good question. Yeah. Okay, so let me say how to do this. Okay, so what I will do is I will say every policy pi that I care about can be written as f of theta, and I'm just going to introduce this notation of pi of theta. So when I say pi of theta over here, it is implicit that pi is some function of theta, and this function is related to the model. Okay, so pi of theta is basically the model taking the parameters theta, outputting this policy pi theta. Okay, so if you compare this equation to this equation, it's exactly the same. All I did is I was like, okay, I want my pi to be expressible by this model. So wherever I see a pi, I'm going to make it pi theta. And this is true just by like definition. Okay, so everywhere I see a pi, I just replace it by pi of theta because I want all these pi's to be generated by my model. And then the other difference is this constant term. So this does not depend on theta, and this other term that does not depend on theta. So maximizing this is exactly maximizing this. Okay? And this is what I'm going to claim is the surrogate function is that I'm going to use. Okay, so it's like kind of tautological that if I care about policies that can be modeled, can be expressed by this model, let me just make this my surrogate function and optimize over theta. Okay. So in order to get to this update, I now need to maximize this function as a function of theta. Okay. So remember, this pi of theta can be like some nasty model, like it can be some like very convoluted neural network, and there is like no way that I can maybe maximize this exactly. Okay, so I'm just going to like try my best to maximize the surrogate, and my hope is by even maximizing this surrogate a little, it does not have to be exact, I can still guarantee that JPy is going to be maximized. Okay. Any questions?
At first glance, I don't see what the surrogate is buying you in terms of making things easier, because you have the exact same term, except
Yeah.
that you did a bit of renaming there.
Yeah, nothing yet. Next slide.
All right.
Yeah.
We are going to show that this surrogate function is, maximizes this surrogate function is easier than the.
Oh, need not be. The claim is going to be even if you can maximize it using say one step of gradient ascent, that is already going to increase JPy. So that's the thing. Like maybe it is like as hard as it was before, but at least even if you make like partial progress, it is going to maximize JPy or like increase JPy. So that's the thing that is on the next slide. Okay, any other questions? Okay, so what is my algorithm? So this is the surrogate from the last slide. I am at each iteration, I am going to form this surrogate. Starting from the previous iterate theta t, I am going to approximately maximize this and obtain theta t plus 1. Once I obtain a new theta t plus 1, I am going to go and form the surrogate again, and I'm going to keep doing this back and forth, back and forth. Okay. So it's like form the surrogate depends on theta via this pi t. So remember, pi t is pi of theta t. This pi t is pi of theta t. So if I give you the parameter theta t, you can go form pi t. As soon as you form pi t, you can form the surrogate LT of theta. As soon as you form LT of theta, you can approximately maximize it. It does not have to be exact, say one step of gradient ascent, and you're going to get theta t plus 1, and that's the loop. Okay, so now the thing is, what changed? So the properties that we want is, one of them is that if I look at this surrogate, LT of theta t, so if I set theta to be theta t, this becomes pi theta t, which is pi t. So this term becomes 0. If I set pi theta to theta t, this becomes pi t. The KL between the same distributions is 0. So this also term goes away. So the surrogate LT of theta t is equal to j pi t. Okay, so it is like tight at pi t. Okay, so it is, and everywhere else, because j pi is what we show is a smooth function of pi. So j pi of theta is greater than LT of theta. Okay, so pictorially, this is the landscape. So I have this function j that I care about. That is the one I want to maximize. And using this smoothness, because j pi is a smooth function of pi, you can show that it is always lower bounded by a quadratic in pi. Okay, so look, it is tight at pi equal to pi t. So both functions are the same at pi equal to pi t, and everywhere else it is lower than this. Okay, and what we show is that the function that the surrogate that we actually care about is even lower than this blue line. Okay, so this surrogate is a valid global, like everywhere, lower bound on the objective that we actually care about. So if I push up my surrogate, I am indirectly pushing up the objective I care about. Okay, so this is like this property of majorization, minorization. So I have found a valid lower bound, and I push up this lower bound, and I'm going to indirectly maximize j pi. Okay, so let's make this a little more precise. So j pi of theta is bigger than LT of theta. So this is this dark black line, and this dotted line is an upper bound on LT of theta. So you have this connection. And finally, suppose you approximately maximize LT of theta. So we started with theta t, and I do say one step of gradient ascent. So I get LT of theta t plus 1 is bigger than LT of theta t. So don't have to solve it exactly. I'm just making some small progress in maximizing this LT of theta. So compared to where I was before, I did one step of gradient ascent, and I maximized it. Okay, and these three together are enough to prove the theorem that I want. Okay, questions before that? Question?
So in the end you're going to use the, sorry, I forget the exact term for that function. I remember what it does, but
Which one?
the upper caps J, the capital
Yep.
J function. Are you going to use that as a surrogate to your?
So LT of theta is the thing that we can maximize because it's a function of theta, and we are going to say that if I maximize this, like even by one step, I am going to improve J pi.
Oh, okay.
J pi, remember, is like the sum of all the rewards that I have, so it's the thing I truly care about.
Yeah, I'm still thinking. All right, what does that buy you in terms of making things easier, if anything? Because
Oh, so the thing that is going to buy us is that we are going to, like, this is a function of theta, so it's easier to maximize. It's like a d-dimensional function,
okay.
right? So this is like, J pi is SA dimensional, so it's like hard to optimize. Theta is something smaller, so it's easier to maximize.
But isn't J a term in that function?
J pi t, so it's not a function of theta.
Yes. So
Yeah.
isn't that the term in the function that you try to maximize?
Yeah, but this maximization is with respect to theta. This does not depend on theta. It's just a constant.
Oh, okay.
Yeah? So it's just a shift.
But okay, it's a constant there, but don't you have to recompute it every time you
So
update
this
your policy,
guy-
every time you get a new theta t?
This guy is the Q function, the quality function.
Okay. Okay, so J pi t is the quality function.
Gradient of J pi t.
And what about J pi t?
J pi t is the value, like the value of the policy.
Okay, so is that some?
Yeah, it's the sum. Yeah.
Okay. Don't you have to recompute that every
It-
time you get a new pi t?
You will, right? Because once you improve, I mean, you don't have to recompute it. It's just like a constant I added to make things line up. But algorithmically, you don't care about pi t, J pi t. Yeah.
Let's move on.
Okay. So, okay, pointer is gone. But okay. So let's do this. Quick question.
So all this rests on the assumption that theta belongs to a set of policies in F, right? Like, so you have all possible policies, and then you have F, which is a subset of that, right?
F of theta is the subset. Yeah.
So, is there any guarantees that if restricting it to the subset will be close to the true J for all policies?
So this does not require that,
No.
but if you do have that, you can actually get to the optimal policy.
Right.
So if you have a neural network, they are crazy over parameterized, there such a property can hold.
I see. So you have to already know this, like.
No, not really. You like choose, so the way these things work is that you choose your neural network architecture to be large enough, whatever large enough means. And then if it is not giving you something that you would want, you will just increase the size of the neural network. So
I guess it's not provably there's no provable guarantee that F will be sufficiently rich to approximate.
no,
So there's
no.
provable-
There is no guarantee that you will reach the optimal.
Okay.
So, but what you can at least guarantee is that whatever you are doing is at least increasing the thing you care about,
Makes
right?
sense.
Like that's like the bare minimum. And if you have like a neural network, you can't prove convergence to the optimal.
Not
So
making
okay.
it worse. Not increasing, but not making it worse.
Exactly, that's like the bare minimum, right? So okay, so so my pointer is not working, so let me do it this way. Okay, so let's prove this theorem by using these properties. Okay, so J pi t plus 1 is J coming from this model pi of theta t plus 1. Now by property 2, J is always bigger than L. Okay, so J pi theta t plus 1 is bigger than LT theta t plus 1. That's from property 2. LT theta t plus 1 is my surrogate at theta t plus 1. I have made progress, so it is definitely bigger than LT of theta t. That is property 3. And LT of theta t by property 1, because my surrogate was tight at pi t, is equal to J pi theta t, which is equal to J pi t. So J pi t plus 1 is larger than J pi t. Okay? And this holds no matter what model you use. Throw a nasty neural network at it, whatever, as long as you can do one step of gradient ascent on it, you are at least improving the policy in terms of J.
JP smooth is an assumption.
J is smooth. It is not an assumption, it is a smooth function of pi. So you can show that that is
Always.
in this discrete action case.
Okay.
Yeah, when you do continuous things, then it becomes trickier, but in this like discrete action case, it's always true. Okay, other questions?
Because it's an expectation.
Yeah, or just like intuitively, if I change my policy a little, does it really change J pi a lot?
Yeah.
So there is like some Lipschitzness property, so
Right,
there is
I
some
guess
smoothness sitting there.
General question is if you have catastrophic events, things are.
Yeah, so in the continuous case, maybe, but in this simple case, okay. So that's kind of cool. So let me see. Let's see if I can do that. Okay. So let's see if I go and actually instantiate this surrogate. What do I get? I get something like this. So this is the surrogate that actually, from an implementation perspective, that I want to optimize for. So these are all the states and actions visited by policy pi t. So this gamma t is a trajectory. So the way to form this surrogate is I take my policy, I interact with the environment, every state action I encounter, I try to maximize, form this function. Okay, so the Q function is telling us how good is action A in state S. Remember, this is the quality. And then I have like some importance sampling ratio in this green box. Okay, and the reason it shows up is that I am collecting data or I'm interacting with the environment using pi t, but I'm asking what would be the surrogate at a different point, which is not pi t. Okay, so I need to pay some like distribution mismatch, and that is given by this like importance sampling ratio. And then again, I have a set of states visited by pi t, and I want to ensure that these two policies, the first one is the policy that I am optimizing for, the second one is pi t. Okay, so these two policies are again close. So this is the objective we actually implement. Okay, so there is like no j pi t, it only depends on this q pi t function. Okay, and then there are many ways of estimating q pi t.
So in your area of research, if you go back to the previous slide, if tomorrow morning I come up with a better L that satisfies these assumptions or propositions, then good to go and try it and publish a paper. And get rejected. Sorry.
I mean, depends. One, it needs to be like computationally tractable. Yeah. So I think that's the key, because there are many ways we can come up with surrogates which are actually better theoretically, but then it's like hard to implement. So getting all three things right at the same time gets you a nearest paper for sure. Like computationally tractable, good performance on standard benchmarks, and good theory. You're good. Yeah. So I agree with that. Okay. So what is this surrogate connected to? So common methods such as TRPO, PPO that people use in practice are all connected to this surrogate. Okay. So in what PPO does, it removes the second term, the scale regularization term, and it says, oh, I'm just going to clip this importance sampling ratio to ensure that I don't move too far away. So if I move too far away from theta t, this importance sampling ratio might become very large, because pi and pi t might become very different. So it's just going to try and clip this and going to remove the KL regularization completely. Okay. But this has its own problems, because you're not doing this in like this systematic way. Sometimes when you run PPO, it can get stuck. So it just gets stuck at like and is not improving the policy because it does not have the guarantee from the previous slide. The other one is TRPO, where you remove this KL from the objective and put it as an explicit constraint. Okay, so that's like another legitimate thing to do, but then the computational complexity of solving this constraint optimization problem increases. So there are like these trade-offs between like compute and like theory and how to solve it. Okay, any questions on this one? Okay, so let me say what is bad about this surrogate. Okay, so the surrogate involves this importance sampling ratio that can become very large. The direction of the KL is called mode CK. So by this I mean if I have this distribution P and I try to minimize that KL, the minimizer picks out a mode of this distribution. So suppose pi t is like not a great policy. It has mass over all the actions, meaning that it says I want to maybe take this action with certain probability, this action with certain probability. If you just narrow down in your next iteration, if you just capture one mode, you have lost all this information. Maybe the correct action that was going to take was maybe over here, and you just hadn't figured it out yet. So you want to like keep some mass over all the actions and not commit too quickly to something which is bad. And this is actually true in practice. This actually hinders exploration. From a compute perspective, even if you have log linear policies, this surrogate is non-concave, which makes optimization kind of tricky. Okay, so a couple of reasons why this surrogate is maybe not ideal. One of them is like more statistical with this important sampling ratio. One of them is more RL, which is this exploration problem, and the third one is more optimization, which is like maybe this is like just a hard problem to solve. Okay. So let me last topic. So okay, so this is the place where we are. We have a surrogate. It is giving us guarantees, but maybe it's not the best thing. So let's go back to the basics and try to come up with a new surrogate. Okay, so this is exactly what you asked. Let's see how I can do it in this way. So the way we do it is we are going to just change the way we think and start treating this Z, which is the logit, as the primary citizen. So up to now, everything was a function of pi, but pi itself can be written as a function of these logits through this softmax function. Okay, so H is a softmax. It takes exponential of Z and just like normalizes them. Okay, so that's the softmax function. And I am now going to form everything in terms of Z by defining G of Z, which is a J of H of Z. Okay, so this is now a composition of pi is a function of Z, J is a function of pi, so G is a function of J of H of Z. Okay, so maybe this is like a very stupid thing to do because I have actually made my problem harder. Like it was already hard, now I have introduced a composition and probably made it even harder. The advantage is that unlike pi, which had to lie on a simplex, Z is unconstrained. Okay, so there's like no projection required. I can just do gradient descent on Z without any projections. Okay, so that saves me some compute. Okay, so what I do, I take the gradient of G with respect to Z, move in this gradient direction, and that's it. Or in other words, try to find the Z vector which is most aligned to the gradient and not move too far away according to this utility. Okay, so this is a new method which is called softmax policy gradient. Okay, and the softmax comes from the Z. Sorry, question?
So we sort of went full circle, eh? We
Yeah.
came back to the expression I had at the beginning just
Yeah.
to,
And I'm going to use this and go through all the steps we did and try to get a better method out. So that's why this like framework not only captures what has been done in the past, but gives you something new. So that's the aim. Okay, so that's like a reasonable thing to do. You stay close to the previous logit while moving in the gradient direction. Okay, so the problem, of course, nothing is free, is that small changes in Z can lead to large changes in pi, or large changes in pi can lead to small changes in Z. So if this softmax function is like saturated, if I change Z by a lot, maybe it doesn't change pi at all. Okay, and this actually happens in practice. From a more geometric perspective, the way to think about it is that the landscape is flat in terms of Z. So even if I change Z a lot, the function that I care about does not really move. Okay, and that's why it leads to slower convergence compared to this NPG approach. Okay, so this is well known. So what we do, let me skip this in the interest of time. So what we are going to do is again the same thing. We are going to start off with this, and now I need to figure out what is maybe a different distance metric between the Z's. If I can come up with an alternative distance metric, maybe I can make this problem faster. Okay, so the distance metric I will choose is this weird distance metric, which is that the distance between z and zt is induced. So every z induces a probability pi. The pi is equal to h of z. So this is a probability pi t. This is a probability pi. So I'm going to measure the distances between z indirectly via the KL divergence of the policies that they induce. So every z induces a pi. So instead of measuring distances between the z's directly, I'm going to say this guy introduces this policy, this guy introduces this policy, and then I'm going to calculate the KL divergence between these two things. And that's like a weird way to measure distances, but it's a legitimate way. It satisfies all the things we want for it to be a proper matter.
So, if I can understand, is this the same as saying you're measuring the cosine distance in a different way?
So this is the KL.
I know, but doesn't that resolve to what you had previously?
In the
Because
opposite
you use
direction.
that, or no?
So now everything is a function of z. So
Right.
that's one complication. But also, I have kind of sneakily flipped the sign of the KL. So previously the KL was pi t.
Yes.
Now I have flipped it to pi t pi.
Okay.
Okay, and this is going to have implications on the next slide.
And you're going to explain why you
Okay, so next slide is how we came up with this. But suppose you buy this and I rewrite this update. So the resulting update is super simple. It's pi t plus 1 is pi t plus eta t times the policy, the probability, times an advantage. Okay, so the advantage is like the quality function, but it basically tells you what is the advantage of taking action A compared to what pi t already takes. Okay, so it just quantifies this exactly, and it can also be estimated by interaction. Okay, so you can just like interact with the world, estimate this A pi t, and throw it into this expression. Okay, so now if we look at this expression, no projections with respect to pi, no normalization, it's just additive. So you're just like literally adding the probability to something else, and that's the entire update. Okay, and this is what we call the SPMA update, or like softmax policy mirror estimate. Question?
So the difference between Q and A is that Q is more long-term thinking and A is more immediate.
No, think of A as a shifted Q. So it's exactly the same.
Shifted Q.
Yeah. So suppose you are in a particular state. If you take action A and follow the policy pi t, you get the Q. You continue to follow the policy pi t, even in state A, even in state S. The difference between the two is the advantage. So it's still long term, but it's like, what is the advantage? So this is called the advantage function in RL. What is the advantage of taking this action in a given state compared to what you were doing previously? Okay, so this advantage.
It's double the effort, but it's
Yeah.
It's 2 times the effort.
Exactly. So it's like shifted, which is why it has like lower variance. But indeed, you have to estimate two things in order to get to this.
Unless you have some kind of fine policy, off policy kind of
Yeah, exactly.
then you plug it into the.
Indeed, exactly. Okay, so that's the thing. So no projections, no normalizations. At this point, you should be kind of skeptical and ask, okay, but why is this a valid policy? Right? The policy should add up to 1. So the choice of eta guarantees that these are all non-negative, and the property that we have is that if I sum up the probabilities times the advantage, so this is like the expected advantage of taking an action A compared to what I took, and that is okay. So if my policy pi t is taking a certain action at state S, some of the actions have positive advantage, some of them have negative advantage. Right? Some are better than the status quo, some of them are worse. But if I just average them, I should basically get 0, right? Because it's just averaging the positive things with the negative things, and then it comes up to 0. So if I sum up across all the actions, this term becomes 0. So then the sum of this is equal to the sum of this. Just like proof by induction. You started off with a valid policy, you always have a valid policy. Okay. Any questions on this?
How will this hold the implication? Like not the implication, the left side of the.
This?
Why is it a sensible assumption?
It is not an assumption, it's a fact.
It's a fact.
Yeah, so this advantage, okay, so think about it in this way. The advantage of taking this action compared to what the policy takes can be positive or negative. But if you average out all these actions, it has to sum up to 0. Like some of them are like +5, -2. Some of them, when you just average all of them, there is no advantage compared to what you're already doing, right? Because you weighed all the positive things equally by all the negative things. So basically, that's the reason why it's equal to 0. So that's maybe one way to look at it. Okay, other questions? Okay, so now this is giving us a valid way to measure or to update my policy. And now why we came up with this. Okay, so another way of writing the same update NPG. Oh, question?
I just think that's an important point. I just want, because on the previous slide, you don't have a definition for advantage, right? So you've gone from SPMA update equation down to rewriting the update. So the property that you're talking about, which is that the app is 0, is somewhat coming out of its definition. But you're giving us that ability.
Indeed.
So you're just saying the way you compute A guarantees that it's
Exactly. Yeah. Yeah.
because
Yeah.
There is a pi hidden there, which is the thing you compare to each pi t, and then you sort of average on it. In the A pi t, there's also another pi that you're comparing to.
Oh no. So it's like compare this action to the action taken by this. So in state S, I will insist I take this action, but the policy pi t takes the action it is always taking, right? That is, like every policy maps every state to an action, like probability of taking an action. It is doing what it is doing. And I'm just saying, oh, if I insist on taking this action, will I be better or will I be worse? Right? And sometimes I will be better, some actions are bad, sometimes I'll be worse. On average, it's basically the same thing.
Wouldn't it be possible that the action that pi t is already taking is already the best possible action?
Definitely.
And then in this case, all the other actions are going to be to negative advantage.
Yeah, and for all those actions, you're going to decrease the probability. Right? Like if this is negative, you're going to make this smaller.
Yeah. So what I'm thinking is about the this sum. If pi t already takes the best possible action, and all the a's are going to be negative, isn't this sum to a negative value?
Oh no, because the corresponding pi t on the best action is almost tending to 1. Right? Like, and that's kind of the cool thing, that if you have already figured out what is the best action, this has already ensured you have put all your probability on that. So it's basically 1 multiplied by the best possible thing plus 0 multiplied by something negative plus 0 multiplied by something negative. So it's all the same.
Then you get something positive. Oh, because there's no advantage of the thing about
Exactly.
itself.
Yeah.
So it's 1,
1, 0, 0.
0 times something negative.
Exactly. Yeah. Okay, excellent. Okay, so where did we come up with this? This is the NPG update, the way it works. One more interpretation is that it is like a mirror descent update. So what I mean by this is that think of this circle as the space of policies, think of this space as the space of logits. So what NPG does, it maps every policy pi t to a corresponding logit, does a gradient ascent step in this logit space, maps it back, and then projects on so that it becomes a valid probability. So this is yet a different interpretation. What the update SPMA does, it like flips this. So you just flip these two things, and you say, I care, my primary citizen is logits. I'm going to move to pi t, do a gradient step in this space, move it back, and this is exactly SPMA. So we designed this metric to measure distances between policies, between logits, exactly so that this interpretation would work. So this guy is basically a dual to this guy. So if this guy goes from policy to logit, this guy goes from logit to policy. So they are like interchangeable. So that's how we came up with this like weird update. Okay. Any other questions? So this is the mirror ascent interpretation. and it is called mirror because the policy space and the logit space are mirrors of each other. So there's like a question.
So, sorry for asking all this. So earlier you said you flipped the direction of the KL term, and I didn't quite catch how that is.
Next slide.
Okay.
Yeah. So okay, so let's just maybe 2 more slides to go. Okay, so let's function approximation. So previously we were parameterizing the policies. Now let's just parameterize the logits. So same, everything remains the same. Our primary citizen is now logit. So let's parameterize only the logit and search in the space of policies that has logits that can be given in a particular. Okay. And we're going to do exactly the same update. So instead of the previous update I showed you, there was no constraint. I was moving in the gradient direction with respect to some closeness between the logits. Now I'm restricting myself to the logits that can be expressed by the model. So exactly the same framework. And the update I will get if I write down this whole thing looks like this. Okay, so this is where things are going to become a little more important. Okay, so what is this? Effectively, the surrogate you get that we should implement in practice. Look at all the states and actions visited by this policy pi t. Calculate the advantage. Again, there is an important sampling ratio, but it is inside a log. So that's going to be good. And then here, the direction of the KL has flipped. So instead of doing KL pi versus pi t, now it is pi t versus pi. Okay. And optimizing the surrogate, same property ensures that it is guarantees that you are going to improve. And for this, you can actually guarantee convergence to the optimum. Okay, so if your log linear policies are rich enough to express the optimal policy, you run this method. It's still non-convex. It's very difficult, but you will converge to the optimal policy, which is kind of cool. Okay, so no time to get into the gory theory. So from an implementation perspective, let's just compare the 2 things. So in red is NPG, in green is SPMA. SPMA depends on the log of the importance sampling ratio. So say the importance sampling ratio is like 10 to the 8. It's 10 to the 8 in NPG. It's just 8 in SPMA. So it's more stable. So this means you can take larger steps. And even though the difference between the policies becomes quite a bit, it's okay because the ratio is multiplied is inside a log. Now, why is the direction of the KL important? Is because of this direction flip. Suppose now I'm minimizing KL, P, Q. So P is again my fixed distribution, and I'm trying to find the Q such that this opposite KL is now satisfied, is minimized. So the probability I get is going to be spread across both modes of this initial distribution P. Okay? And this is exactly what you would want, maybe because initially pi t is not sure, so it has mass spread out across the actions. So you don't want to eliminate some of the actions, so you want to like spread the mass, and this ensures that you don't commit to a bad action early on in the optimization. The last thing is that if you care about log linear policies, this surrogate, if you rewrite it in yet a different way, is actually concave, and it is similar to multi-class classification from supervised learning. So that's the punchline, that you can convert an RL problem into a sequence of multi-class classification problems. So it's like you have your policy pi t, you go interact with the world, collect all this data, write it down as this surrogate corresponding to SPMA, solve this multi-class classification problem, and that gives you the next policy that you should go and interact with. So you just take this RL problem into a sequence of supervised learning problems, each one of them looking like multi-class classification. Okay, and that's like a very nice reduction because we know how to solve multi-class classification, so that's kind of helpful.
Does this mean that heuristically I can replace this softmax expression with LDA, QDA, all these multi-class?
Exactly, yeah, so it gives us a lot of scope to play now.
Right.
Yeah, that's right. Okay, last thing, a question?
So there's two problems. So there should be 2 separate problems or something. And one of the KL divergence is the mode covering. So as long as we switch those, mode covering is okay.
Yeah.
is there any value, so log, so it smooths it out. What about using more aggressive smoothing? So I guess what you're saying is, like, as long as it's differentiable,
Yep.
wouldn't it'd be fine.
It
right?
would be fine.
And all the properties would hold.
Don't know.
You don't see.
Yeah, the log is because it's compatible with like the softmax, so that's where the log shows up.
Sure.
Like the way to move from logit to policy is the softmax,
Oh, I see.
but the way to move back is to take the log transform. So that log is that
I see.
log.
So to get the last property, you need the log.
Yeah.
But if you wanted smoothing, you could use any.
You could
property
use,
function,
yeah,
I guess.
indeed. So what people started doing is they said, this is the log, this is kind of annoying, let me just approximate the log by like some Taylor series expansion and see what it does.
Yeah.
So that would be like.
Cool, thank you.
Okay, last slide. So here are two games. For which we ran these methods. So one of them is like a shooting game. So this is all of these games are Atari games. There are like 50 of them. We ran it on like 20 of them, and they all look kind of similar. So this is one of the games. It's a shooting game, and this is like a Pac-Man type game. So in both of these, the score is basically the score of the game. So on the y-axis here is the score, or like the reward you have accumulated. In orange is SPMA, like this surrogate I showed you at the end. In blue is the national policy gradient surrogate. Okay, so that's like the first one we discussed. So they are kind of compatible here. Orange is better than blue there. And all these, like PPO is the method people use to train these large language models. So it is sitting in green. And sometimes, like I was saying, it just like stagnates unless you like go and tune the hyperparameters again. And then in red and purple are like these TRPO variants, two of them, and they are also not good. So, and this is all with like standard hyperparameters that we just borrowed from these repositories that have like sat down and tuned everything, and then you just like take those and you run it, and this is what you get. So like kind of doing well. And to me, the cooler part was in order to implement this orange line, we made no changes. Like what I showed you in the theory is exactly what we implemented. So no hacks. Okay, so that's the end, thank you. So we did a systematic way to construct surrogates, ensured monotonic policy improvement, and developed this method, SPMA, that has good empirical performance without additional heuristics. For future work, what we are doing at the moment is how to handle constraints, right? Like you can't do, if you want to deploy this on a robot, you want to maximize this reward, but you can't like fall off a cliff or something, right? Like you need to have a systematic way to handle constraints, and this broad field is called like safe RL. So that's what we are looking into at the moment. I did not talk anything about exploration, so you want to explore the world, but do so in a way that still leads to higher reward, but still figures out parts of the state space which are otherwise hard to reach. And finally, the application my student is looking into is like, now we have all these methods for Atari games, maybe we should try to do something more useful. Can we do reasoning with large language models? So yeah, I'll stop there. Thank you so much.
So the handling constraints one. The bottleneck here seems to me the log of the probability ratio. So could you like train a neural network to approximate that, incorporating those constraints, and then instead of having every time to sort of compute it, you just plug in whatever happens, and then it's constant evaluation. I mean, obviously, there's a pre-training with respect to the
Right.
Feasibility problem.
That's right.
But that ostensibly might be kind of easier because it's all about exploration and not about reward.
So people in robotics do what you said,
Right.
kind of. So they have like these controlled barrier functions,
Yeah.
which basically tell you that you should not move here.
Right.
And those are either available to you or are like pre-trained or
Right.
trained before you start interacting. And then there's like a notion of like whether you would go from like training in simulation to actually like running the robot. So yeah, that would be like one thing to try. So like I have this student who is, we are collaborating with a robotics person, and yeah, so this is the thing, yeah, we are trying.
So can you comment on generalizing to continuous optimization? So like the theta parameterization
Right.
seems to move in that direction, right?
Yeah, so at this point, this was this parameterization in all the discrete things we were doing is like some neural network that basically outputs a set of probabilities. In the continuous action space, you say pi of a given as theta is modeling the mean and the variance of a Gaussian. So you consider like a high dimensional Gaussian, and you say what is the mean and variance of this, and those are the parameters to tune. So you can put pi of a given as theta as like a Gaussian policy, and that also works. So there is like these continuous control tasks where you need to train a robot walking in the environment, and basically there the actions are how much force I need to put, what is the velocity, and so on, which are more continuous things. So Mujoko is the suite of these problems, and we tried it there, and indeed it just works as is. So you just replace the softmax by a Gaussian, and it's all the same. So that's what we have been doing with continuous.
Yeah, would you say that your method is more sensitive to hyperparameter tuning than some of the other methods that you showed?
We did a test early on, kind of similar. I was actually hoping it would be less sensitive, but kind of similar. So that problem we haven't figured out. But the two parameters that we have to tune is this eta, and then how you optimize this surrogate. So optimizing this surrogate, we can make it adaptive, so you don't have to tune anything there. So then it's a matter of like tuning this like one parameter. But yeah, like performance does vary quite a bit depending on how you set eta. So I am wanting to get rid of that. Yeah, that's a good question. Yes.
Yeah, for the evaluation, could you go to that? The comparison between different ends. So would all these 5 methods ends up with the same reward, or like the SPMAs ends with like higher reward than PPO or other methods?
So you mean for the other games?
I mean, for let's say for this game,
For this game, the reward for the orange line, which is SPMA, is higher.
I mean, by the end of the day.
Oh, so this is like 10 to the 7 interactions. So it's a lot. Yeah, and I don't know anyone who tries to do more. I think as a community, we have kind of set this to be the threshold. Because you do need to run like 10 seeds with this, so if you want to get like confidence intervals which are like reasonable.